Okay, so I think it's time to start the afternoon session. So we have two talks before tea break and this talk. I think should start probably. I don't know if I have the authority to start it. I'm looking at the organizers.
Yes.
Okay. Should I wait? Wait? Did you say wait?
No, I said go ahead.
Okay. So our first talk is by Moncrieff from NCAR. He's going to talk about organized convection, whether it's just climate intersection, and the YOTC project.
Thanks. Well, thanks to the organizers for inviting me here. It's a pleasure to be back. This is my second time in Bangalore. Last time was in the monsoon season, and so that's quite a different climate. Anyway, this talk, I think, will be slightly different from what I was aiming to do. The reason I decided to do this is because we haven't really talked about the subject I'm going to be speaking about a bit. That is a kind of a new development around the world, actually. This business about bringing weather and climate together. You young guys will certainly be involved in this for your careers, I guess, much more than right now. Before, weather and climate were very separate things. One was initial value, the other one was boundary value. But now there's a much more outgoing look at the whole thing. And seeing how weather varies in the climate timescales is a big deal. And also the extended range of weather prediction. Huge problems. So that's why I say here that's kind of an objective, that's a long-term objective. There's also an important thing developing because of increased resolution, and that is the changes in how we approach convective parameterization. That's another serious issue. And so I'm going to be, and a part of that is, climate models with mesoscale resolution. A lot of that is driving this sort of thing. And the YOTC project is just a part of this. So that's where I'm coming from. I think it's worthwhile telling about what the mesoscale is. It's not a scale. It's a range of scales. And this whole range encompasses most of weather, almost all of weather, actually. So, and the 100-kilometer scale is very significant because of huge amounts of energy and momentum get exchanged on that scale. And the point that, of course, is, the grid scale is not the resolved scale. So if we're thinking about resolving the mesoscale in the global model, we've got to think of a 1-kilometer mesh. We're nowhere near that, except in a sort of experimental sense. Certainly not in a predictive mode. So, but we are very close to the 10-kilometer mesh. We're there almost with global NWP models, and getting there with climate models. So it's interesting to see what this means. And this is why I say we're entering this new era. I can't overemphasize that. Where the mesoscale permitting global models are almost with us. And the fact we need new approaches to a difficult problem already, the convective parameterization. So what is organized convection? Well, you know what it is, you guys. I mean, cumulus parameterization really only deal with this. We're trying to deal with that. Others are mainly larger scale organization. And in between, there's all sorts of things like tropical cyclones, mesoscale systems, supercells, tornadic storms, and so on. But getting there is by no means easy. We can't just resolve it away right now. So this is kind of a picture that shows us where we are at this present time. With climate models, I mean, there's still pretty much 100-kilometer grids, a few experimental higher resolution. But the weather-climate intersection, that timescales of weeks to months, we're kind of in this area where, 10 kilometers almost are there. And experimental climate models are run with, a few of them, not many, at that resolution. Of course, climate and weather models are very different because you've got a lot of data assimilation in the weather model, but almost nothing in climate. And this is where we reside with this mesoscale organization problem. but we do have cloud resolving models, of course, had some for some time, that resolve the mesoscale, but not completely on the global scale. And we have very, very necessarily dynamical models. And those are incredibly important. And it's kind of a feature of this conference, actually, this sort of thing. So that's where we are. And I should say, this is where a huge range of difficult problems lie in monsoons and so on. And getting to this is a very exciting part of, I think, of the meteorological spectrum. What I'm going to do is see where we can get with looking at we call a building block of lots of weather events, the mesoscale convective system. And I'll go on to some other things later. But it's an interesting multi-scale problem on its own. And you know pretty much what it looks like. They populate the tropics and mid-latitudes as well. And in fact, we know more about these systems than any other meteorological system, I'd argue. I found this a very interesting diagram. It's the fraction of tropical rain from TRIM that comes from mesoscale convective systems. The red area here, brown is about 90%, and the reddish area is anywhere between 70% and 90%. And we see it picks out all the major convective parts, the ITZZ, Africa, South America, and also the Bay of Bengal, you may note. And, of course, the monsoon region. So we can't, the mesoscale system is not an isolated thing. It's compounds, so also say Central Africa, which is slightly different from the Western Africa. So we cannot say it's just a thing on its own. The mesoscale convective system interacts very directly with all scales, really. And the fact that they provide more than half the tropical rainfall, probably more actually, really it must be a key part of the water cycle in the tropics and other places. And the point about these systems is that they transfer energy upscale and downscale, depending on the dynamics and so on. So they're a big deal in maintaining the tropical circulation. Part of this is because one of the things is the convective heating is elevated because of the stratiform heating and so on, and the downdraft cooling. And it's got a large horizontal extent. It's not just one cloud. It's hundreds, thousands perhaps of cumulonimbus during MCS life cycle. And this is about configurated momentum transport, but I'll say a little bit about it. Now, the very nice thing, we have excellent knowledge of this. From theory, observations, and simulations. But we still can't predict it. Isn't that interesting? Or global models can't. The reason, no, climate models are even in a worse state. Because actually, these systems don't exist in global climate models. Because the parameterizations are not up to the job, and the resolution is not quite good enough. I'll show you a bit about resolution in a minute. I'm going to another thing, which is kind of a frightener, I always found, but never mentioned, the scale gap. Present parameterizations assume that things in this area, 1 kilometer and a bit, cumulonimbus, are separated from the synoptic, order a few hundred kilometers by a gap. This allows the parameterization schemes to be a single column, and there's no lateral transport at all, and so on and so forth. It's kind of forgotten. When you develop things like entrainment, parameterization, it's totally forgotten this fundamental point. Because mesoscale systems, as we just showed, populate this region. So we have to deal with this. Now, dealing with it is not a simple matter, because this is the traditional parameterization. Oh, that should be, the grid scale is bigger than the convective scale. Something happened. Explicit. If we are able to resolve, say, have 100-meter grids, we'd be in good shape, I hope. But at the present time, the grid is getting, close to in fact, some of the systems are bigger than the grid scale. So we can't, we're in trouble. Or we were. We're still in trouble with the traditional climate models, but we know that we've got a whole range nowadays. Large eddy simulation, cloud resolving 1 kilometer models, i.e. mesoscale resolving, and to some extent the 10 kilometer models. So we're in this area now, and in fact the next generation climate models, getting there, and so on. So we're kind of got a lot of tools here, but this is what we're stuck with. The parameterizations are kind of like this. I mean, you can get a little bit more than this, but it's much more. Isolate updrafts, downdrafts in a column, compensating descent. But these mesoscale systems are dynamical systems on their own, and they've got shapes and fluxes and so on. But they're also they occur with cumulonimbus. But the point is, these circulations are not represented in any sense. This is more than just, what is meant here. Cape, you know about the convective wave potential, that goes in here quite a lot. That's what drives most parameterizations. But there's actually another two interesting kinds of energy that MCS-like system, propagating systems, can call on. There's Cape, of course, but there's also this business about pulling energy away from the mean flow and using some of that. Or the other way, putting energy back to the mean flow, upscale transport. But there's another thing here which is also forgotten mostly, the pressure gradient. These systems are not updraft, downdraft, they're actually hydraulic systems. They're driven very largely by the pressure gradient. So we have to account for the pressure gradient in some parameterization. U-naught is the flow in the cloud relative to the propagation. This is the relative flow, just relative flow. I want to get from these three kinds of energy. And we know a lot about this. I've done a lot of work on this one. But mechanistically, we know how these systems work. And indeed, these energies are all taken into account. And from solutions to the equations like this, which is almost exact, by the way, for 2 dimensions in steady state. So we can calculate these things. So I'm going to go. I'm not going to dwell on this. But the only approximation you really need in 2 dimensions to take the full sets of the nonlinear equations and get it into this form is this approximation. The buoyancy is some function of the vertical velocity times could be a complicated function. And therefore, you can write this thing as a complex equation. Not complex, a complicated equation. But anyway, what I would like to do now is, how are we getting on with resolution? Well, I just thought I'd go back to the climate thing again. The AR4 report, and the AR5 will be exactly the same, I'm sure. The regions that have no certainty at all are sort of in what will change over the next century or whatnot. Are actually in these regions here, the white regions. Or I should put on this. The white regions, for actually the summertime U.S., northern winter part of South America, so on and so forth. Africa. I found this an interesting thing. Some years ago, actually, Lane and Fritsch made a very interesting diagram. You see these regions, the gray regions are regions of orography, and this is where MCS has occurred, and that's the mean flow. That's the U-naught. So I'll just take up the U.S. for a minute. This is where these systems, for example, develop. And Africa is a real hot spot. So what about simulating this? Well, this is a cartoon of what we need. The Rocky Mountains of the U.S., for example. Rocky Mountains are here. Convection develops into multi-cumulonimbus system and then propagates. Can we do anything about it? The very important thing here is always forgotten too, vertical shear. I've never heard that mentioned at this conference much, apart from Andy. Yeah. Yeah. But as a prediction, oh yes. But you guys didn't emphasize it. I'm joking. Yeah. I'll say nice things. I'll say nice things about you in a minute. Yeah. No. This is a week-long. This is nice. Over the United States, we have propagating systems, and this is observations from radar. These red things are mesoscale convective systems. With a cloud in a mesoscale resolving model, actually it does a quite a good job, especially some cases. Even the 10-kilometer explicit one does a reasonable one. And if you add parameterization to this, it doesn't do much. In fact, the next diagram shows you the total. This is the total precipitation in that simulation. See, what parameterized convection does, all it does is kind of lightens up the diurnal cycle. They come on every day. But the systems that propagate are resolved, or partially resolved. Okay? So with 10 kilometers, it's not, 10 kilometers. This is just an example. There was quite a complicated simulation of this, by the way. I'm not going into detail. But 3 kilometers, 10 kilometers, you look at the flow fields. Just look at these trajectories. They look similar. They're a bit weaker in 10-kilometer grade, of course. But at 30 kilometers, totally different. Wrong. Not the right kind of systems with some sort of cumulonimbus sitting on a gravity wave or something. So between 25-kilometer grids are kind of dodgy for mesoscale systems. If you look at momentum, that really shows it up. This is the momentum transport calculated from these simulations. And it's all this is moving that way. The momentum transport is negative here. At 10 kilometers, it's weaker, but proper sign. 10 kilometers at 30 kilometers, rubbish. So 10 kilometers is getting there, but not quite right. So what we need to do in a parameterization is interesting. You would need to somehow represent this what comes out from the parameterization. The propagating convection gets that. But that's not a simple thing to do. But it's got a simple possible solution, because we know from many theory and others and numerical simulations that the two modes. There's the vertical mode, that's the half sine, and this is a full sine for the heating. And there's a alpha 2 is the ratio between those quantities in terms of heating, and alpha 1 is the amplitude. So that is the kind of type of formula you need. And in fact, I think that's what's in you guys' models. But this is not in prediction models. Momentum same. Not same, sorry. But you can reduce what it looks like. Propagating that way, low-level acceleration, other way, upstairs, so to speak. Now, I'm going to show you some of you may not have seen. I had a PhD student which I helped supervise at Scripps Institute, Mike Pritchett. And so, having done this over have these United States reasonable success, we say, well, why not try superparameterization? Superparameterization is where you run cloud-resolving models instead of ordinary parameterization. It's not ideal, but it sure gets memory and so on. So this is just one diagram. It just summarizes what was the case. This was a superparameterized community atmosphere model, 3.5 actually. CAM 3.5. With I don't show this, but this has also been published. Standard CAM, there's no mesoscale system. It doesn't exist. It's like that climate thing. No rain from these systems over the United States. With SPCAM, propagating mesoscale system. And this is an example. These are just snapshots. See, this is time. This is the diurnal cycle, 0 to 18. Oh no, a diurnal cycle, yeah. So these are just some examples. This is the cloud outlines, if you like, and this is the propagation. And it varies a bit, but it also varies in observations. And it's about the same range. And these are these propagating systems, you know, anvils, downdrafts, and so on. There is a slight thing I need to say about this. Superparameterization, the CRMs are all periodic domains. So if you develop an NCS in one domain, it just comes in the other side. It doesn't propagate, you know, across. However, what happened here was we found out that, in fact, we did get the CRM to communicate with the large-scale grid. The reason is that, go back here again. Remember I said about this? This. If you put heating, heating cooling dipole in a shear flow, you get a organized flow. And so what the superparameterization did, it created the heating. The grid scale shear actually did the job. In other words, the shear interacted with the heating on the, you know, more than the mesoscale, and the propagator.
Could you see it in the heat tendency of CRM? Or
Pardon?
I mean, what you are saying is that second Berkeley mode has been, I mean, it's
Yes.
substitution from
Right.
CRM. Could you see it in the heating tendency from the CRM, or is it conjecture?
No, we look. I haven't shown it here, but the MCS is on the multi-grid. Looked like they propagated, but they didn't have right structure. That's in the paper, by the way. They're a bit distorted. And that's a problem. You can imagine that because, but okay, I'll not go into that. Yeah.
So your summary on superparameterization is what?
The superparameterization does a great job on getting the propagating systems. It's got a memory. It doesn't switch off and switch on again every time step. It propagates. It's got a slightly wrong large-scale heating because the heating is the interaction shear with the heating is not quite right. But it transports momentum quite reasonably well. No, we tried both. It didn't matter. If you think about it, it doesn't surprise me.
Well, in this case, though, you have an orientation because it's downslope convection.
Yeah,
So it's east-west.
there are caveats, yeah. But actually, we were surprised. We thought they'd be, you know, poorer job than that. Anyway, I'd like to go into a little bit with the Mad-Julian oscillation. And that's a much more difficult problem in terms of scales. But you know, it's kind of like this. 1 kilometer, 10 kilometers, 100 kilometers, 10,000, a whole lot, really. So what I'm going to do is summarize where we are with this. And one model has done a great job with this in the last 6 years, well, actually more, actually less than that, 5 or 6 years. ECMWF model. I'll say imperfections in a minute, but in 2000, we want to get a signal like this. This is a hindcast sort of thing. If you look at 2010, this is a total core test case. We see that the heating, here is the OR, in fact, is pretty good. In 2004, there's hardly any coherence at all. There are caveats. This is with like all models. The ECMWF does a good job. If the MCS is ready there in the analysis, it can keep it going for a month.
If the MGO is there.
Yeah, I'm sorry, the MGO is in the analysis. Can keep it going for a month or so. But starting it up, you know, if one is not there, real problem. Another problem is the maritime continent. Somehow the parameterizations or whatever it is, maybe it's more than that, over the maritime continent disrupts the MGO too much. We saw this a few years ago with even a lower resolution version of the model. These systems actually, even at coarse resolution, get resolved. These are super clusters, big and MCSs. Now, climate models have a real problem. This is a recently completed intercomparison of aquaplanet models, and this is for the tropics. There's no truth here. We don't know what an aquaplanet should look like in terms of convection. But this is a cloud resolving model, a NICAM global CRM. And we see this easter propagate, maybe not the right wave number, but nevertheless, easter propagate. The other ones, these are serious, these are top-class climate models. But you see, you just need to look at this. I mean, it's all over the place. Eastward, westward propagating, stationary, single, where's the single column? Oh, these are single column storms. So they've got a real problem. They're looking up, though. But one thing I'd like to show you is an example about CNT from the NICAM. The NICAM is the Japanese really measure-scale resolving model. In this case, this is 3.5 kilometers, global grid. Gets things like hurricanes and, reasonable-looking towers. But is it right? Another PhD student from the University of Tokyo, we got interested in this. And so in the NICAM model, there's a reasonable, MJR supercluster-like structure. And I think there's 40 days of simulation, 35, I can't remember. There's a whole this is a snapshot. These are propagating, this is squall lines, if you like. They're not orientated all the same direction, because some are slightly angled, and some are east, west, and north, south, and so on. But there were 13,000 shots of this. So statistically, it's reasonable. And this is the summary of this thing. This is the red is the east is the westerly, blue is the easterly, and this is the vertical momentum transport gradient. Oh, well, I should look at this. The tendency. The tendency is for the westerly wind burst to accelerate to low level. That's what you expect from convective momentum transport. So what we're saying here is that these global cloud resolving models get a pretty good regional. This is only 7 kilometers. This one actually. So it's, it's fairly coarse resolution, but it gets a reasonable cloud life cycle on the mesoscale, which feeds back on the large scale.
The scale looks very big on this system.
What?
The scale,
Sorry.
Scale,
This is part of the domain. Yeah, this is minus 50 to 50. Yeah. It's degrees, 50. Yeah.
So that's very big.
Yeah, big. Yeah. Mm-hmm. Yeah. The place was analyzed was in here. Yeah, it's a big deal. Yeah, it's a huge. It's an NGO scale. Yeah. Okay. But the place is analyzed is sort of in the this region. As we expected, and we have a lot of theory on this. We should expect this to be, the tendency to be exactly like this. We're a bit uncertain about what's going on up here. You only can keep a certain amount of data on these big models, and we didn't keep data on the cloud heights. This part may be part of momentum transfer, or maybe gravity waves. In fact, it could be. Anyway, we're going to do another one with high resolution soon. But this is what the sort of summary of this thing is. We know from this sort of theory and also multi-scale theory, Andy, and you're talking about CNT, the backward, if you propagate in that way, backward tilt has this eddy like this, negative momentum transport, and the negative, the derivative of that is the tendency, positive, negative, and that's the sort of thing you get. So the CNT effect is really strong in this case. Maybe too strong. I don't know. We really don't know what the answer is, of course. No observation. Well, we do have some observation, but not enough.
Mitch, you went too fast. Could you flip back to the slide where you showed it?
That one? Mm-hmm. That one?
Yeah. No. The one with the profiles.
This one?
Where is your U prime W prime?
This one.
Yeah.
This one.
U prime W prime is there.
Yes. I should add, there is some north-south too. But like this is the U prime,
You've got
which is
W prime D prime too.
yes, exactly. There's some of that. Yes, there is. That's MCY. That's this one.
Isn't U prime W prime in the upper right plot?
Yes, that one.
EX, right?
Yeah, that's right. Maybe this. Yes. Here,
If you
YX.
look at the bottom, you can see the U prime, W prime, and Z.
Yeah. Yeah.
Okay.
Yeah. Well, no. All you need to know is that this is the right sort of. That's what we expect from U prime W prime, even at 7 kilometer grid. So I'd like to say a little bit more about this CMT business, because Sam talked at length about this, and I agreed with you. He did, because he agreed with me. Okay, yeah, and this is a simulation that actually isn't this the White? This is the first super parameterization, I think. YOTC developed super parameterization, invented, so to speak. Yeah. And this was in a full model, starting from a state of rest. Perturbing it randomly. There was 2 series of waves that developed. One was a sort of a wave number 4, kind of convectively coupled wave. We don't know what it is. Really, it propagated too slowly to be really, Kelvin wave, anything like that. But the point was that after about 40 days or 50 days, it began to think about itself a bit, and there was a formation of Rossby gyres, and that Rossby gyres had a big effect. And as part of this is a single mode, a single, disturbance. It's an MJO-like thing, and it has this significant circulation. Where does CMT come into this? Well, there is an interesting thing about Madden-Julian oscillations, which have really not got much attention, and that's the business of what's called super rotation. They can accelerate the super rotation if the atmosphere is moving faster than the Earth underneath. Okay, and we don't know how much in terms of observations there are on this, but there has been observed actually. We were talking about this last night. So this is this is from the YOTC simulation. We have this is a solid that's westerly, and this is the first 40 days. You see, there's a negative and positive. This is just U prime, no rho here, so this is a bit exaggerated. This is per unit volume. So per unit mass, it would look more realistic. This is what the simulation gave for the U prime V prime. This sort of shape. And indeed, over the whole range of this scale, the parameter range in this archetype, you got the same shape. What this does not do, this kind of model, is predict where it's coming from. It's a mechanistic model for the fully developed system. So we need to know what is going on. How did they get there? This is something that I think we need to take a bit more seriously. This trio, actually, with a multi-scale approach, put in this the momentum fluxes on the small scale and tested out how the large scale responds. In a nutshell, the way that this gyre forms, in terms of momentum, is that the heating on the synoptic scale, rather than the mesoscale, and the momentum transport on the synoptic scale conspires really to drive the mid-ion circulation. And this was very nicely done in this paper, I think. And the theory here for the CMT is what was talked about yesterday. And there's a lot further to go with this, particularly in this multi-scale situation, and with the Madden-Julian oscillation. So that's where I'm saying that the theory of the mesoscale momentum transport on the mesoscale and the synoptic scale, I think we understand where we are. We don't quite understand fully in terms of Mann-Julian oscillation. Oh yeah, this is another example of the superparameter. This is done by by Marat. I should have Marat here, and with no ordinary parameterization. There's no propagation, but indeed, these mesoscale type of systems develop with the superparameterization. I'm going to finish up by mentioning something and say why we're doing it on this topical. I've been spent a lot of time on this with Duane Wallace. It's the idea here is to really use high resolution global prediction models to get an estimate of the global circulation and how convection and other things work in that. We call it a prototype because as the model, for example, the NWP models assimilate an enormous amount of data these days. Each of them does something like 40 million pieces a day, so on. So that's the observations. The model is doing a decent job fitting the topics with Mann-Julian oscillation, which is great. And so what we thought, well, okay, we're trying to develop. We started. Oh yes, this is just a summary of what this ECMWF YOTC data set is. May 2008, 2 years. This is a test case, 2008 to 2010. Oh, that should be 25 kilometers. So what's a kilometer? Yeah. We have a full global analysis. That's, in other words, 6-hourly global analysis. 10-day forecast with 3-hour type resolution. And very importantly and uniquely, the 30 subgrid variables, the subgrid densities. Convection, heating, surface fluxes, Q1, Q2, you name it. This is the real bit that takes the time and energy, if you like. The actual global analysis and the forecast just comes out as the model is running. As the model generates its forecasts, this can be archived. So this bit is fairly, standard. Getting this stuff here is a bit more, time-consuming, energy-consuming, storage-consuming, and so on. So, but we're moving forward with this, and it's being analyzed by several people. We had one talk here. There were lots of other ones. We're getting about 50 publications on this. So we've seen. Oh yeah, the 3 parts of this. There's the global prediction. That's the high-resolution modeling, which I just mentioned, analysis and so on. We also have and a lot of this is due to Duane, satellite, huge amount of satellite information. And we've got NASA to actually have a one-stop shop for people who don't understand how to do, analyze satellite data. Can use what's known as Giovanni. But mostly the profiling satellites: TRIM, CloudSat, Calypso, AIRS, that kind of thing. It's very easy to use. It's really nice. And I say it's done by NASA Goddard. And this is the research part. All I'm going to say about the research part, what we're doing kind of with a collaborative effort. And this is what I'm going to say, yes. Here we go. Oh, this is the framework of the what do you mean by virtual? We got all these satellite observations. A lot of it's dumped into data assimilation. With field experiments, you can't do a global field experiment. It's impossible. So, and this is the best thing we can do is have all these NWP models, high resolution, getting the global, the global picture of this, and it sort of complements real field or actual field experiments. That's what the YOTC concept is. We have 3 publications in this, and the August BAMs may or may not have seen this. But anyway, what I'd like to show you is two model intercomparison efforts that's going on. One is in the YOTC 2-year period, we had La Nina and El Nino conditions. The first one has been analyzed in one project and this one is in another. This is by far the biggest one, the green one. We were very fortunate during YOTC because we had 2008 and 2009, which are a normal monsoon and a pretty poor monsoon. So we think we can make some, and in fact this is ongoing, but some people in this room. But what I'd like to get back is the NJO. This is almost completed. This one. This is where you run climate models in weather prediction mode for 5 days. So that the hindcast mode to see how the model. We're trying to evaluate how the models are doing. There are not so many. There's 8 modeling groups in this one. It's mostly European effort. This one is done by the Met Office. The next one is a really interesting one, and it's not finished yet by any means. And the reason why we're doing this is this problem. The diabatic heating by the Madden-Julian oscillation. This is three recent analyses effort. The ERA, Interim, MIRA, and CFS. This is the rainfall. The black line is the rainfall anomaly. It's the same on each. But you notice that there's quite a lot of difference in these ERA interim things. MIRA and interim, and the CF, they're all different. Either in the amplitude of the heating, and in fact, this is the active part of the NGO. This is the inactive part, suppressed period. It's also the height of this, and also the distribution, the amplitude, and the height of the maximum. That's a big deal, because the gradient of the heating is, would drive a lot of this tropical circulation.
What do you call that?
It's what's called Q1. It's the calculation of the latent heating mostly. No, that comes from the models. Yes, we need to know how good these reanalysis are.
But if MIRA gives Q1 directly, right?
Was that? Sorry?
In MIRA you get Q1, right?
Yes.
But you don't get Q1 in MIRA interim.
That's in what?
You don't get Q1 directly from MIRA interim, right?
No, that's right. Already some difference.
Kind of from CSSR.
That's correct.
Now, question is that
Yep.
Yep. Yeah. So
I know
whether
that.
that is
That could be. We don't know that yet. In fact, if that's an explanation, that's fine.
So the explanation is there's not a direct inversion. You need a secondary.
That's right.
solving step
That's correct.
for most of the data.
There are assumptions made, and maybe the assumptions explain all of this, but nobody's done that, so we need to know that. Another thing is this one this one here is latent heating derived from remote sensing. That's a much more problematic area because there are assumptions made on the heat, how you get the heating from the the data sets, and there's much more variety in that. These are two. I'm not so sure what train is actually, but this one here, these were derived from using cloud resolving models, for example. So we need to understand what's wrong with this and can they be improved. Because we'd expect that the reanalysis, the high resolution model results should be better than that, should help us in the development of this. To improve these retrievals. And this is a big thing. It's not finished by any means. But we have also some global cloud resolving models putting in efforts in here. So that's where we are. Oh, yes. There are 3 kinds of calculations with this. There's the climatological, the 20-year simulations. Oh, sorry, is that one? Yeah, this should be 20-year. Yeah, somewhere here, is that? Anyway, yeah, and the short-range hindcasts, and the medium-range hindcasts, 20 days and 2 days. And these are the Madden-Julian oscillations. These are 2 Madden-Julian oscillations in the 2009 period. El Nino situation, and these are integration times. So I'm finished now. Really, what I'm just going to conclude This business of bringing mesoscale processes to climate models is a long-term issue. But as opposed to a few years ago, the climate community is really getting interested in this. It's not particularly in the using the the climate models in forecast mode, and that was what was these intercomparators were about. There's another thing here. There's a lot of pressure these days to find out how weather is varying on the climate scale. I mean, come on. But it's questions being asked. And we can't even address these questions unless we can have some measure of what weather looks like in models. So as I said, young guys, you'll be hopefully involved in some of this. And this other thing, the big one about bringing dynamical concepts to convective parameterization, that is really interesting. And it's about time. It's about time because the parameterization, not great deal of progress has been made in the last several years. Certainly nothing in bringing the mesoscale into the problem. But it's even more necessary as the global models get to higher resolution. 5 kilometers in 20 years' time or something. Or 10 years, I don't know. But the global climate models, none of them will ever have, not ever, in the foreseeable future have cloud resolving resolution. So we're not going to get it for nothing. Got the answers for nothing, I mean. So we're making some big progress in this. Higher resolution models, dynamical theory, both mechanistic and multi-scale. And that's really important. And CMT is, I think, we're moving forward with this. This has been a neglected thing for too long. And it's, I think that one is really, I think that's going to really come forward fast. There's business about vertical global, the YOTC approach. I think we're only starting on this. I mean, as I say, it was a prototype, a 2-year shot. But as the models, I mean, the ECMWF model in 1 year will have 10-kilometer grid. So it's getting back exactly to our target here, where we're going for 10 kilometers. So a lot of individual investigations going on. I don't know all of them for sure. But these 2 major international ones are really moving forward. And we had a good response. Something like 30 or 40 global models, global model centers involved in this. It'll take a few years, maybe 2 or 3 years to, yeah, I'm finished.
Okay. Thanks, Nick.
Yeah.
So we have time for a few questions.
So, I have one question about the simple part of the YOTC campaign when people were doing 5-day forecasts. I would like to know, because we know there's a lot of publicity with the great MJO that ECMWF has, and I don't believe it, because when they do a Wheeler-Colades diagram, they get only westward power, and I think you hinted to this, that when they know there's an MJO, they can propagate it.
Yeah.
So is there a group of people in YOTC with 5 or 7 day lead times, not knowing there's an MJO, in the reanalysis there was an MJO, and what's the predictive skill of that?
Yeah, well, no, I mentioned these papers. That's actually,
are they addressing that?
Yes, it's actually mentioned the problems the ECMW have with remaining problems are laid out one by one.
So there's a paper on it that's available?
Yes, that's right.
Thank you.
The one in BAMS. It's a summary.
The one in BAMS.
Yeah.
Thank you.
Yep.
First slide, first transparency.
The first one.
First transparency, whatever you showed first, the very first distribution of clusters or whatever it is.
I'm not sure what you mean.
Transparency in your projection, the very first projection.
Oh, the very first one?
Yes.
Oh.
In which the clusters also, this is not different. No, over the map of the world, global map.
It must be an easier way to do this.
I am asking only question which is centric. That one went away. In any case, yeah, that one.
This one?
It's before that.
Next one?
No, before that. Trim data. Trim. No, I don't know. Trim distribution of.
No, you're going back.
I don't know what you mean. No, that one. Yeah.
No, I am only asking you with respect to the India-centric question, the monsoon question.
I'm sorry, I can't hear.
I'm only.
Is that thing on?
What India-centric?
Oh, yes.
India-centric question.
Yes, oh yeah. Mm-hmm.
You have a big cluster of that red
Yes.
over the North Bay of Bengal.
Yes.
And then along the monsoon trough, you see it is decreasing. The red circles are decreasing.
Yes.
Isn't it?
Yes.
So the convection by and large over the North Bay of Bengal, is convective rainfall.
Yes.
Isn't it? And as you
NCS
enter
type,
inside,
actually.
it is the combination of convective and the stratiform rainfall.
Mm-hmm.
Isn't it?
Mm-hmm.
And there are years when the convective rainfall over the Bay of Bengal decreases, and there are years when it increases. When it decreases, it is not able to penetrate into India. See, there is convection taking place over Bay of Bengal, slightly less, but the years of drought are those in which the convection is occurring over the Bay of Bengal. It is not penetrating it inward. That means it is not transferring itself into the stratiform type of convection, and as such the rainfall is suppressed over India.
I see. Mm-hmm.
So, I just wanted to have your opinion about that with respect to the convective and the...
Well, yes, I mean that's a long question, a long answer, I bet. This area here is full of propagating the convection system. Some come off the land, some come up this way. But I don't know. I haven't looked at it.
They farm a lot over there.
They don't.
They farm a lot over the Bay of Bengal. Warm water.
Yes.
So is having saturated city. At that point, they go on farming, popping up every day, every second day, third day.
Okay.
Like that. And the drought years are distributed like that, where the distribution of that changes in the sense that over the Bay of Bengal, the convection becomes less and the penetration of convection inland is reduced.
I see. Reduced.
Yes, reduced, much reduced.
Mm-hmm.
And that can lead to much reduction in the stratiform rainfall.
Okay.
The rainfall over India, 50% is contributed by convective and 50% by the stratiform.
Yep.
The 10 data we are in live.
Which is this sort of type of thing.
No,
Yeah, this.
the central part of India are the Gangetic plain. The rainfall over that plain is crucial to us. Is 50% convective and 50% is stratiform rain. The transformation of these convective rain over Bay of Bengal into the stratiform rain, what is the cause of that?
Well, it's probably the life cycle of METEOROLOGY. I mean, that's exactly the sort of thing. I mean, it developed over the Bay of Bengal, but die out over land. But the convective region goes on for a long time. You can even get some there's certain vorticity, keeps vorticity developments. Keeps the stratiform region going for a long time, several hours. So that's probably what it is.
One last question.
Okay. Well, I presume that the year of tropical convection is over, isn't it? 2010.
In 2002, 2 years, yes. Yeah. At the moment it is, yes.
At the moment it's complete. Well, I just wanted to bring to your attention, you probably know it, this new Indo-French satellite.
Bigger topic, yeah. Mm-hmm.
Yeah, which is now started.
Yes.
Data are out,
mm-hmm.
and I think they will or are already available. A very large part of the data are available internationally. Yeah. So I think that on the tropics there will be a lot of new data with a frequency of several per day. So complete diurnal cycle can be done as well.
Mm-hmm. Yep.
Profiles, humidity, and radiation budgets and so on.
What needs to get into the global models.
No, my question was going to be: do you see a good way of using this data through scientists here or elsewhere to further the objectives that you've been describing here.
I think in the it's 10 north to 10 south, so it's quite a fast turn time. I think it'd be an excellent thing to do, to evaluate where we are with this. In fact, the ECMW probably assimilates some stuff, but not a lot.
Okay, ECMWF I think will sooner or later get instead of a direct assimilation into the models.
Yeah, but I think to evaluate the present models would be an excellent thing to, right now even.
Okay, let's move on to next lecture.